So, welcome student to the next class of Introduction to Nonlinear Optics and its application. So, today we have lecture number 52. So, we will be continuing with the old topic that we have started in the last class, that is the parametric amplification process under 4-way mixing. So, in parametric amplification process what happened, then in optical fiber we launched a pump omega p, and if this optical fiber having a third order nonlinearity which is quite strong, then what happened, we can use this as an amplification of a signal omega s. How this omega s will be generated can be understood by this energy diagram, that two pump photon will going to absorb and will generate one idler photon and one signal photon. So, that means omega p plus omega p will be equal to omega s plus omega I. Since three waves are associated and we are generating omega s out of that, so it is essentially a 4-way mixing process, and in this 4-way mixing process the important thing to find out the evolution of the electric field containing frequency omega s, that means the signal, the corresponding source term. So, PNL omega p is a nonlinear polarization term that will going to excite the omega p field or the pump, and in order to consider this pump field, we only take the cell phase modulation term because EP is quite strong. So, since it is quite strong, I will only consider its own interaction with itself, that is the cross phase cell phase modulation. The cross phase modulation term with the other effects omega I and omega s is neglected because they are quite weak. In a similar way, if I want to find out the source term for signal and idler, we only take the cross phase modulation with the pump and also the 4-way mixing term related to the pump. Here the 4-way mixing term related to the pump is the second one. Both the cases we have taken these two terms. So, why these terms are taken is important, and I believe you can understand that why these terms are taken, because there are many terms in omega s frequency. Omega s frequency can be generated in many ways. With the cell phase modulation also we can generate by combining 3 omega s, omega s star, es star and es also will generate omega s. Also ei star, es will also generate omega s, but we will not going to consider these cross phase modulation and cell phase modulation term because they are weak. Only consider this cross phase modulation with pump and 4-way mixing. Well, if I now make a total picture of whatever we are getting, then this will be our a summary. So, it looks quite heavy, that many equations are there, but if you look carefully you will find these are merely the identical equations written. Only thing that is the frequencies are changed. So, let me explain one by one. Do not get confused with so many terms, it is quite straightforward. The first, I have written the definition of our electric fields, that EP is defined by half EP e to the power I kp z minus omega t plus complex conjugate. In the similar way, I write E omega and Ei. This is the definition of the electric field that we have been using for several times. So, EP, so E omega p, E omega s and E omega I is known. Next thing that one should know in order to calculate the Maxwell's equations is the corresponding source term. Source term also I calculate in last slide, and these source terms are for PNL omega s, PNL omega p and PNL omega I is this. In the first case with PNL omega we are having only the cell phase modulation term. In the next case we have a cross phase modulation term with EP and the 4-way mixing term, and for idler we will have the same thing. So, now I have the electric field or corresponding source term. In this portion I just wrote all three Maxwell's equation that you can use. First case, how the pump will going to evolve is shown. In the second case, how the signal is going to evolve is shown. In the third case, how the idealizer is going to evolve is shown. Here there is a slight mistake, it should be omega p, it is written omega 1, it should be omega p anyway. In the next slide, in the next part of this slide, in this portion, we write the compact form of this Maxwell's equation. We know that this term will, there are many terms that will cancel out, and if I take the slowly varying envelope approximation, we will having this term. I meticulously write half both the cases, so that you can have the idea that every term will multiply it by half, because according to our notation this half is already there. And also the p nonlinear terms, in the right hand side is the derivative with respect to p nonlinear. So, it will be p nonlinear omega with mu 0 omega p square, because when I make a derivative of this quantity, only thing that will come out is omega p if I make a derivative with respect to t. In this case it is omega s square, it is omega I square with a negative sign, all the cases. So, these are the compact forms of whatever the equation we have. So, now we just replace here whatever the source term we are having and generate the corresponding field equation rather. So, let us try to find out what should be the field equation for the pump, because pump has a source term which is cell phase modulation kind. So, cell phase modulation, the solution of the cell phase modulation, we know how to do that, but let me do once again, let us. So, it will be 2I kappa p 2I kp dep dz. So, if I go to the previous slide, basically we are using this equation, right now for omega p, evolution of the omega p. So, this half term will cancel out with p nonlinear omega p, which is this. So, we have 1 by 4 term here. So, eventually you have 3 by 4 term here. So, if you look carefully, we are getting 3 by 4 term here with a negative sign, mu 0 epsilon 0 omega p square chi 3 as usual, and apart from that we have EP square EP mod square EP, and this is a phase matching. The phase matching is automatic. So, exponential term will not be here with both the term, from both the side it will cancel out. So, we will, this leads to an expression like this. This is the equation of pump. What should be the equation of signal and idler? You just use the same logic or the same procedure, and if you do, you will find that I will going to use, this is some sort of exercise I want the student to do, that I will going to use these two equations where p nonlinear of omega s is given, p nonlinear of omega I is given. So, I just put this value, make the derivative. Basically the derivative is not required at all, because of the derivative we have already have omega h square and omega I square term, and when I put this term together, we will simply have this quantity. So, first term is corresponds to the cross phase modulation term as usual, and second term is a corresponding phase corresponding for a mixing term. The exponential term will modify, because in the right hand side we have e to the power I k z, it will come this side. So, that it will, we will have 2 kp minus ki minus ks. So, this is the our phase term. In the similar way we will have an expression for idler. Now, if I this coefficient, if I write kappa, which is 3/8 omega j chi 3 divided by njc, and now this j is running can be getting the value p, s and I, and in that case it will be kp, ks and ki for these three coefficients. Then in the right hand side we have a more compact form, and this compact form is dep dz is I kappa p ep mod square ep, which is a straightforward cell phase modulation kind of equation. In the next case we have a cell phase cross phase modulation equation with a 4-way mixing term, and the last case also I have a cross phase modulation with EP and the corresponding 4-way mixing term. So, the next thing is to solve this equation. So, now we are going to solve ES. In order to solve ES, we need to know what is EP, because EP is sitting here and we have a solution of EP, we can have a solution of EP here. If we do the solution will be something like this, and this is nothing but the solution of cell phase modulation. So, you can do quite easily, just put EP as UP e to the power I phi p, and if I put this here, you will have an equation of UP, which is amplitude, and equation of phi p, which is a phase, and divide it into two parts, real and imaginary, and on the right hand side I can also have real and imaginary. If I combine these two, real and imaginary, we have two equations, one for the differential equation of amplitude and another for phase. We will find the amplitude will not going to change, but there is a change in phase, and if we put this together, then we will have a solution as shown in here. So, this will be our solution for EP. So, now once we have the solution of our EP, and you can see it is not going to evolve because it is so strong that it can be considered as a constant, but since it is cell phase modulation effect is there, so we should not consider this as a constant, its phase is changing, maybe the amplitude is constant, there is no evolution in amplitude, but phase is changing. So, we need to consider this phase term here in this third order effect, which was not there in second order effect, because there is no cell phase modulation kind of terms are there. The next thing is we just put here, I have EP. So, what I will do, I will put this EP here and EP here to rewrite the expression of ES and EI once again. If I put these things together, then my ES and EI, the differential equation of ES and EI will slightly modified, and it will be like this. Please note that now this additional phase will be inserted here. So, e to the power I k z term was always there, it is a natural phase term, but on top of that we will have another phase, and which is coming because of the fact that my pump is now having a phase term. So, this phase term will be added here. Next, in order to reduce all these terms, I write delta k plus 2 gamma p p is big gamma. So, the equation for differential equation for ES signal and idler is something like this. This is the compact form of differential equation, but still we need to solve this two coupled equation, that is something which is important here. So far we are dealing with the differential equation of ES and EI, but here we have a differential equation of ES and EI, but not only one term, there are two terms associated with that. One is corresponding cell phase modulation term and another is the 4-way mixing term. So, cell phase modulation and 4-way mixing terms are together, which should be, because this is the demand due to the physical process, this will be there. So, in order to solve this coupled equation, we will going to have some sort of transformation. So, transformation is that I write two new variables AS Z and AI Z star. Why I take AI Z star? Because in those two coupled equation you can see that one case it is ES, but in another case it is EI star. So, I take AS as ES e to the power of 2 I k s E p mod square 2 Z. This is the transformation I took. Also for AIZ I took another transformation, which is EIZ star e to the power 2 I kappa E p square Z. Why I took this transformation and why this is the we took this is this particular form, you should know right now, that if I now make the derivative with this transformation, if I now the derivative of A is with respect to Z, in the right hand side it will be ES dz minus 2 I k s E p mod square E s and e to the power of 2 I kappa s E p star z. Now, this quantity, if I look carefully from here, ds dz minus of 2 I kappa s E p star E s, if I put it here. So, I can this quantity I can replace as I k s E p mod square E I star e to the power I gamma z. So, this is the term I replaced here. So, this term and now d I dz is now simply becomes I kappa s E p square E I and with exponential term like this. This now I write E p, I know what is the solution of E p. So, E p is mod of E p square is here. So, next thing is I just replace this E I from here, so that the entire equation become in terms of A s and A I. In the right hand side now I have E I and the left hand side I have A s. E p is a constant, so we shouldn't bother about E p. So, I will make E p as usual. So, I kappa s E p. If I now change this E I star from here, this E I star will be A I z star, which is this, multiplied by e to the power of minus 2 I kappa s E p mod square z. So, if I write this term, it will be exponentially, this term will combine and give exponential gamma minus 2 kappa s E p square minus 2 kappa I E p mod square z. So, this is the final expression we have in terms of A s. So, in terms of A s, now I have this. Now, equation of signal and idler we want to derive. So, this is the expression of A s which corresponds to the signal. So, beta is now another constant I want to introduce, so that I can reduce this part. So, if I reduce this, all things are constant because E p I consider constant, it is a strong field. So, E p is considered. So, when I put this, so we have a rather compact form for A s. If you calculate the compact form of A s in the similar way, you can calculate the compact form of A I also. So, A s and A I are the fields corresponds to frequency omega s and omega I. So, now I write the differential equation for A s and A I with this particular form. So, this now allow us to solve. Now, we are in a position to solve this differential equation, and how we solve this? This is the old equation, old kind of equation. We have solved this in the previous classes. So, we make a derivative both the side of A s. So, here we have a derivative of A I. So, this A I derivative I will replace from here, so that the equation become in terms of A s. Another term is also appearing from here, which is e to the power I beta z with I beta and A I. So, again I will replace this A I from this equation, and I will get a more straightforward expressions. So, as I mentioned, so what we do that we will make the derivative with respect to A s. So, when we make a derivative with respect to A s, there will be two terms. So, one is this, which is a constant. So, d I dz will be here and plus I beta A I star and e to the power I beta z will be there. So, this is the derivative with respect to z for both the side A s. Next, what we will do? I know that A z is this. So, I will replace this here. I will replace this term here. Once I replace this term here, so this become a function of A s. In the left hand side, I will have A s. So, our goal here is to eliminate A I, because then only I can solve the differential equation. So, I just decouple the equation. Now, we have A I star. So, A I star I just replace A I star, because I have dAs dz is equal to I kappa s mod of EP square and then EI star and then e to the power of I beta z. That was the expression we have for As. Now, what I will do, I will just replace this AI star as simply 1 divided by I kappa s EP square e to the power of minus I beta z multiplied by dAs dz. I will replace this term here. If I replace this term, this is the term after replacing. So, now you can simplify these things, and when I simplify we find this is the differential equation we have in our hand. So, if this differential equation is there, now I write kappa s kappa I EP whole to the power 4 as g square. So, I will have a differential equation of As, which is a signal amplitude in this. Next, we will going to solve this equation, which is not a big deal. So, if you solve this equation, so I can solve this differential equation. This is a homogeneous second order differential equations. I believe all of you who are taking this course are quite enabled to solve this equation. So, I am not going to show how you solve this, but if you solve this differential equation, you will going to get an expression something like this. So, I ask the student to please solve this equation by your own, and once you do that, you will get a straightforward solution in this particular form. So, this solution, if I write these things as k, so again I replace the different variable to make it more compact to another variable. So, I just write g square minus beta 2 divided by 4 whole to the power half is k. So, my As is now c e to the power k z plus d e to the power minus k z e to the power beta z by 2. So, this is the way the signal will going to evolve. So, the boundary condition is that when As at z equal to 0 is 0, we should have a, if you remember the figure, we should have a small amplitude of signal. So, this small amplitude we say E is 0. So, E is 0 is C plus D, which is, so if A is 0 is E is 0, then C plus D will be 0. If I put the boundary condition, then Z equal to 0 becomes C, Z equal to 0 become D. So, C plus D, this is 1 will be E is 0. This is the first boundary condition. The second boundary condition is the derivative of this quantity is 0, because A I at Z equal to 0 is 0. So, that is why the derivative which is containing A I, or rather A I star, is 0. So, I will have C minus D this. So, I have C plus D this quantity, C minus D this quantity. So, with these two boundary condition I can eliminate E and D. If I eliminate E and D, then finally we have the expression of As, and this expression of As basically, if I put this D, E and D together, C and D, whatever the value of C and D we have, then from here I can eliminate D by just adding, and I have a value of C, and I can also eliminate C by just making a minus sign. So, I will put this here, and after putting that, if I manipulate slightly, then these two equations, the A's become this. So, this is the solution of the signal under 4-way mixing. This is the solution of signal under 4-way mixing. So, we have a cos hyperbolic term k z plus I beta k sin hyperbolic k z term, and then e to the power I beta z by 2. Next, I want to find out what is the corresponding power. So, I know that power is proportional to the fields square, and A, if you go back to the transformation, you can see that A and S is related in such a way that mod of A S square is equal to E S square. So, amplitudes are same, only the phase term is associated with this transformation. So, once we make the mod term, so this phase term will cancel out. So, I can readily write it is E S, it is E S 0, and if I take a mod term, I will have this quantity. So, if I make a ratio, then this ratio E S Z divided by E S 0 square will give me the ratio or the amount of gain. This is the efficiency, that if I have P S 0 as input and something we have at Z point, then if I make a ratio, then we find that this ratio is greater than 1, that means we have some sort of amplification. So, this ratio gives 1 plus G square K square sine of K Z. So, this is basically the gain term, that is gives you, this is a non-zero positive term, that means we are getting some kind of gain out of that. If this term is not there, the ratio is 1, that means there is no gain, whatever the value we have at Z equal to 0 point for P S, the same value we have for Z, and this gain value will get a maxima when there is absolute phase matching, that is beta is equal to 0. For beta is equal to 0, we have a maxima of gain, which is sine hyperbolic square G Z. So, this is the standard expression for gain for 4-way mixing in optical fiber. So, we just derive these things and understand that how the parametric amplification can be generated in optical fiber, and there are certain phase matching conditions. So, beta is equal to 0 means we should consider a phase matching condition, but if you look carefully, you will find that in this phase matching condition, the phase associated with the field, phase associated with the pump field is also there. So, the field related, the pump basically acquires some kind of nonlinear phase that should be compensated by the propagation vector of signal and idler. So, this nonlinear phase matching is important to generate the efficient amplification. In fiber, we can readily match this phase by just changing the dispersion profile, and we have a 4-way mixing gain. So, today we learned these things. So, in the next class, we will go further and try a different application of 4-way mixing, and that is the phase conjugation. So, with this note, let me conclude here. Thank you for your attention, and see you in the next class, where we explore more on 4-way mixing and learn a new concept or new problem related to phase conjugation. Thank you, and see you in the next class.